is you have to clear out the shipyard while you take your x-rays. Oh, that's not what I wanted. There we go. Let's see. Well, I can't get enough intensity. I'll just pass it around. You can hold it up to the light, and you know you can see bad welds. Okay, you really need a high intensity lamp. But in any case, by 1995, the NAT David Taylor. Anybody know what David Taylor is? Yeah, what's David Taylor?
It's an empty research building right across from the Naval Academy.
That's David Taylor Annapolis. Is an empty facility. I used to spend summers there in the 80s, part of my summers. But currently David Taylor, the big David Taylor is, as you go around the Washington Beltway at about the 930 position, when you cross the Potomac River from Virginia into Maryland, right there on the Maryland side of the Potomac River, just west of the Beltway, is the David Taylor model basin. And David Taylor was some ship designer, I don't know, from 150 years ago or something. But anyway, the Navy Ship Research and Development Center which is NAVSEA's main laboratory. The Naval Research Lab, which has turned out a number of Nobel laureates, is the Office of Naval Research's research laboratory. And the David Taylor Model Basin, or the David Taylor Ship Research and Development Center, is the Navy's NAVSEA's research laboratory. And Patuxent, Maryland is the NAVAIR Research Center. Okay, so each big group in the Navy and in the Air Force and everything else has their own research center. I mean, the big center for research in the Air Force is Wright-Patt, okay? And actually Wright-Patt is sort of the basic research and the, what they call 6-1 and 6-2 money. 6-1 money is basic research. The 6-1 laboratory of the Navy is the Naval Research Laboratory, where they're studying astronomy and things like that, for obvious reasons from the old days of navigation. But they were one of the leaders in developing the GPS. Okay, GPS was because they wanted to do navigation, but it got to be more than that. Anyway, David Taylor is what they call a 6-2 lab, and these are actually pots of money that Congress gives out. The Congress says you can spend so much money on basic research, you can spend so much money on exploratory research. So David Taylor is the 6-2 lab of NAVSEA. They also do a lot of the 6-3 and 6-4, which is advanced development is 6-3, and prototype or something is 6-4, and there's all these different pots of money, okay, in the accounting, the DoD accounting system. In any case, David Taylor in the mid-90s had done enough work, and ultrasonics had come along well enough that they said, instead of doing radiography in shipyards, you have your choice. You can do x-rays or you can do ultrasonics. Well, immediately, all of the civilian shipyards switched over to ultrasonics, okay? Because it was cost effective. You didn't have to shut down that area of the shipyard while someone brought out a iridium-192 radioactive source and everyone had to clear out for 50 yards around. You had to have 2 people doing the radiography and 10 people security to make sure that nobody except rats went into the radiation zone, right? And they probably are trying to protect the rats too nowadays. In any case, the Navy shipyards, the ones run by the Navy, they didn't want to do ultrasonics because it would decrease the employment, okay? It would save money. And that's the last thing a Navy yard wanted to do, because these are civil service folks, right? These are their buddies. So actually I had a Navy student do a thesis on this, okay, about 6 or 7 years ago, about why the Navy yards didn't switch over, okay? And he didn't say it quite as bluntly as I just did, but there was no good reason not to switch over to ultrasonics. So yes, today ultrasonics is the X-ray method of choice for heavy section welds in a shipyard, because NAVSEA did a lot of work at David Taylor to prove out that ultrasonics works just as well and can find flaws just as well today as X-rays. Okay. But and it also leaves a permanent record. Now that we can store reams of information, you can store the whole ultrasonic test. In the old days, one of the things that people wanted to do is they wanted to store the reference radiographs. On a pipeline or something, you have to keep, or a nuclear reactor, you have to keep those radiographs for the life of the nuclear reactor. So 30, 40 years or whatever, you have to keep your quality control records. Nowadays, with ultrasonics, you can keep them on a disk drive, right? It might be terabytes, but you can still do it. So anyway, so see, you give me a question and I can run on with it for a while. So yes, ultrasonics is the method of choice in your generation, but you only have to go back 15 years and it wasn't the method of choice because it wasn't even allowed. It was only about 15 years ago that NAVSEA made the change and said you could use UT rather than radiography. Okay. And then you run into the politics of which shipyards would adopt it. The ones that were trying to save money or the ones that were trying to spend money. Okay. There's important lessons there for you if you didn't know these things. Okay. So far as that goes. Any other questions? Okay. One thing I'll pass this around. I should have brought it before. This is 2011 edition of lightning protection systems. I handed out the paper about Ben Franklin and lightning protection systems, and this is what Ben Franklin has evolved to. So now it's 70 pages of how to design a lightning protection system for your house or any other building, or an ammo dump or something like that. There is one, I think, a separate standard for marine, so if you got a sailboat or an aircraft carrier, when you're out there in this middle of this big flat ocean and you're the tallest thing around, you actually need a lightning protection system because you're going to be where it strikes. There's nothing else around for it to strike. It's always it wants to strike the highest thing around, and you're the highest thing for miles around, particularly if you're an aircraft carrier. Okay, so you have to have a good lightning protection system, but it's very highly engineered nowadays. Okay, and basically a lot of these standards end up becoming design rules. Okay, that's actually where I started this course. Is if you think you're going to design something, they tell you how to design it in the university, but they don't tell you about all the restrictions on your design. Well, if you're going to design a lightning protection system, that tells you how to do it. And if you don't know anything about how to do it, it tells you how to do a better job than Ben Franklin did. But it also sometimes stifles innovation. Okay, for example, the boiler and pressure vessel code, we're still using 50-year-old steels. And the reason we're using 50-year-old steels is because it would cost several hundreds of millions of dollars to qualify a new steel. We have better steels now than we did 50 or 60 years ago, but essentially things are grandfathered in. If you look at medical implants, polymers that go in the body, back in the early 70s, the Food and Drug Administration came out with a law, or the Congress came out with a law for the Food and Drug Administration about medical implants. They were becoming more prevalent, and they basically grandfathered in all the plastics that had already been used successfully in the human body, things like polylactic acid. Well, why would polylactic acid be compatible in the body? Well, it sort of breaks down into some of the components of milk, right? It's lactic acid, right? But that's why people had chosen it. Polyethylene, which is extremely inert. But people have done a lot in plastics over the last 40 years, but there has not been another plastic certified for use in the human body since the early 70s, because the law basically set down the specifications of what you had to do to certify a new material. And it's so, all these, you're going to have to go do, hamster studies and dog studies and monkey studies, and then you're going to have to do, it's going to take years and years and years, and nobody can afford, so they always try to engineer around the existing materials that are acceptable. So in that sense, those are two examples of specification stifling innovation. Okay, so if nothing else, hopefully you'll get an idea that specifications are good and specifications are bad. Okay, they're good because they tell us how to. A lot of experiential design rules. You don't have to make the same mistakes as a lot of people who went before you, but they're bad because you can't innovate. No one's going to let you take the risk. Okay, and so somehow, someday, somebody's going to have to resolve that issue. So we've been talking about some of. I got to get it back down to a reasonable light level. Okay. So different codes and standards and who writes the codes, and we talked about costs and things. Just to give you an example, the reason I brought some of these codes and standards, I mean, this standard is reference radiographs, and actually there is a written standard that you can find in a book, and it's all of 2 pages long. But then what goes with it are all these reference radiographs. I bought this for probably $200 or $300 back in the early 90s. It now costs about $500 or $1,500. Okay, so because people have decided to make all kinds of money. What I did this morning is I went and, to give you an idea how specifications have grown in size, this is the 1979 structural welding code for steel. This is the 2010. Okay? And you can bet that almost every line in this new one is the result of some lawsuit. Someone made a mistake, they ended up fighting about it, and after about 3 or 4 or 5 years, someone comes along and write something else into the code to explain things. And that's where we left off the last time, where I said you should only get what you pay for. And I put this up at the very end, which is actually out of the structural welding code. It's been there for a long time. But if you if you decide you want something other than visual after you basically wrote your contract and said, I just want visual inspection, and you decide you want to do some destructive inspection, it says that the owner shall be responsible for all costs of this, but the contractor has to do it. Okay, the contractor can't refuse to do the extra inspection, but the owner has to pay the extra money because it wasn't in the contract to begin with. Well, this comes up all the time. What happens, and I'll give you an example of 60 Wall Street is a 40-story building in New York City, and it's J.P. Morgan's building. And on the 7th floor, they have their computers for trading, stock market trading. If they lose those computers, they can start losing $1 or $2 billion a minute. Okay, because of all the you're dealing in small changes in price, but on huge sums of money. And if all of a sudden your computer can't keep up with everybody else's computers, you're not going to be able to do your trades and swaps. And people are talking, nowadays we're getting down into milliseconds, of interest, okay? Believe it or not. So anyway, they built the building on a very rapid scale, inspection schedule. And so they're not inspection schedule, but on erection schedule. And it was a 40-story building, and they were building the riser pipes for the air conditioning system, which I remember like 16-inch pipe. Okay, it's just 16-inch water pipe goes up 40 stories. And if you start calculating the pressure of that, you know how to calculate the pressure head, I assume. Okay, but of a 40-story building, which is about 400 feet at 0.44 pounds per per foot or whatever, you're going to have a couple hundred psi on the ground floor of this thing, and a couple hundred psi inside a pipe is of 16-inch diameters, a fairly high pressure. Well, they were building it so rapidly that as they were putting the steel up, they were also welding these pipes in place, the vertical pipes in place, and they got it all built. But the inspectors didn't want to go out there on walking on the I-beams and stuff, so they didn't do a lot of inspection of the welds on these riser pipes. And for whatever reason, about 10 years into the system of the building, someone had some reason to look at one of these welds. And you're welding a pipe, so you're only welding from the outside, and the question is, did you get enough penetration through the thickness? And they found the welds were lousy. Okay, well, of course they're lousy if you're on a rush job and your guy's up there hanging off an I-beam with no protection around him, no wind protection or anything else, and he's trying to weld, and he knows the inspectors are 10 floors beneath him and won't be up there by the time he's done, and off the top. Okay, so there wasn't a lot of incentive for the people to do a really great job. So now they realize we've got some really lousy welds in our riser pipe. What do we do about it? Because if we lose our air conditioning system, we can lose $1 billion a minute. Okay, so the building was sort of height-wise went up to about the 10th floor, and then stopped, and then the other 30 floors went above it over here. So they had this little ledge area. So they spent $7 million to move one of the air conditioning compressors, and the air conditioning compressor is about the size of this room, and they had 7 of them in the building. The designers determined they needed 2, so they put in 7, okay, in the basement. This is sort of the J.P. Morgan way of doing business, okay? If you need 2, you buy 7, okay? So they took one out of the basement and they put it up on the 10th floor ledge on the roof to cool the computers that were on the 7th floor as a separate redundant air conditioning system, so that if they did have a leak in their riser pipe and they lost all the air conditioning in the rest of the building, they wouldn't lose their trading floor, okay, because there was too much at risk. Well, then they got into a fight with the contractor of who was going to pay for not only the $7 million, but the other $20 million, which was going to be to repair all the rest of the riser pipe and replace it. So they got into a big fight. And what had happened basically is they had only bought visual inspection. And these things passed visual inspection. They looked fine on the outside, but they were crap on the inside. I mean, you go a quarter, if it's a ½ inch pipe and you go a ½ inch in, there's no more weld. It's only a ½ inch weld, not a ½ inch weld, okay? So anyway, they ended up with a big fight over that. That type of fight comes up, at least I end up getting involved in a fight like that about twice a year, okay, where someone discovers something. This thing that I talked about, the oil company with their 600 links of pipe, they found one leaking pipe out of 600, and they decided that they were going to rip out everything they had already put into their refinery, and a $3 or $4 million thing, which could have been solved by $100,000 worth of inspection, turned into a $60 million lawsuit, okay, because someone said, rip it all out. A lot of times you get a manager who thinks, I'm going to get this other guy to pay for it, so I'm not going to take any risk on myself. I'm going to just rip it out and then sue them for the difference. Well, it doesn't work, folks, okay, because the other people sometimes will decide you had to be reasonable about what you decided to do. But that's why the codes triple in size. That's why the codes in a 20, 30-year period, that's why the people who sell the codes, the for-profit people, have decided this is a gold mine for them, okay? So you should only get what you pay for. That's why should is in quotes, because, you can try to go to court and get something else beyond what you paid for. That pipeline inspection, I think I already mentioned to you that the flaw, if you do a destructive test or even a non-destructive test, the hydrostatic test, which was required, sort of equivalent to visual for a weld. The hydrostatic test might only require 40% of the wall thickness to be good quality. But if you go do these non-destructive tests, they're surrogates for an actual stress test. I mean, a hydrostatic test is a real proof stress test on the pipe, and it'll tell you how much load that pipe will take without bursting. And so it's sort of a measure of real manufacturing flaws. Whereas the non-destructive tests, things like eddy current, okay, things like X-rays, things like magnetic particle, they will find flaws, but then you have to determine whether that flaw is significant. And that's the difference between NDT and NDE. Anybody know what those two acronyms mean? NDT is non-destructive testing. NDE is non-destructive evaluation, okay? So a non-destructive test, that's what something the technician does. He goes out there in the world and he does a test, and he finds not a flaw, he finds what's called an indication. And that's the non-destructive test, to find that indication by whatever technique. Then the non-destructive evaluation, someone has to come along and interpret it. Well, do you think the guy who actually runs the X-rays knows how to interpret it? I mean, he can say, well, it's bigger than this standard, what's in that little green book back there, right? But in terms of doing an engineering interpretation, well, actually, those guys can do an interpretation, as this thing says, to see, a lot of times they can tell whether it's an artifact of the X-ray or the ultrasonics, depending on its surface roughness or surface gouge or something, rather than something internal. Whether it's a false indication or non-relevant or relevant. If it's relevant, now you get down to NDE, which is the evaluation, and you really need someone with some engineering training to come in and determine whether it's if it is a flaw, is it acceptable or is it rejectable? And that depends on what's the stress level, what's the environment, how much wear allowance, how much corrosion allowance. Well, obviously the guy who runs the X-ray machine can't tell you any of those things. And so it really has to be some sort of engineering type person who can do the NDE based on the finding of the NDT, so far as that goes. Anyway, and they follow that to you take any one of these codes, not any one of these codes, but many of these codes, like the structural welding code for steel or aluminum, it tells you what's an acceptable indication or a non-acceptable indication. And we talked about an eighth of an inch flaw or indication was typically what is allowable in many codes. Now, I remember, it's about 20 years ago, I came back from Japan, a trip to Japan. I'd been gone 1 or 2 weeks. And I get back and I have a note on my desk to call this company down in New Jersey. I think it was Engelhard, makes precious metals. And they were building a catalytic converter for the 747-400. The 747 comes in different dash numbers. I think they're up to the dash 900 now or something, but back 20 years ago they were building the 400, and this was an extended range 747. So they can go to longer routes, okay? You can be even more miserable on an 11-hour flight than a 9-hour flight. First time I ever went to Japan, we had to stop in Anchorage, Alaska, because you couldn't go all the way across the Pacific. They did a great circle, and you'd stop in Anchorage, you'd see this big polar bear stuff there, and you'd hang around for an hour and a half, then they'd refuel the plane and you get on. Well, coming out with something like the 747-400, you could go from Los Angeles to Sydney, which is one of the longest city routes on a great circle in the world, okay? There are 2 or 3 that are longer, but now the 787 Dreamliner can do any of them, any major cities. They don't have to go further anymore unless you're the Air Force and you want to go all the way around the world in one trip without refueling. But in any case, they had a titanium welding problem. Did people know there were catalytic converters on an aircraft? They're there for the air you breathe. when you're up there, there's a lot of ozone up at 40,000 feet. And if you were to breathe that ozone, you would get a headache on one of these long flights. So they actually take the air that's coming in when you're flying up there, and they put it through a catalytic converter, just like in your car, to get rid of the ozone. Okay? So you have 2 catalytic converters on a 747. Forget the engines, it has nothing to do with that. It has to do with the air you breathe. And so they have these pipes, a dual system, in case one of them breaks down or something, I guess. And they had been making them out of stainless steel, and they decided for the extended range they had to save more weight, so they're going to make them out of titanium. Okay? And I used to do titanium. My first welding contract for the U.S. Navy was back in the 1970s, was welding of titanium. So I knew something about welding of titanium. I get this phone call. They were not able to meet the Boeing specs. There were 4 welds in this catalytic converter, and they were getting a 50% reject on the X-rays. Okay? And if you got to make 4 welds and 50% of them fail, and you only have 1 chance to repair, we weren't allowed a third option to repair. You can start figuring out the statistics of getting 4 good welds on one of these things. And all of a sudden, it was getting to the point it was going to hold up the whole rollout of this aircraft, which at the time was a $100 million aircraft, to be a $250 million aircraft today. Okay, but it was an expensive aircraft. All these orders and Boeing's reputation were on the line, and here little old Engelhard couldn't meet the Boeing spec. Well, what was the Boeing spec that was so critical here? Well, the story here is the spec made no sense whatsoever. Somebody at Boeing, who was obviously not really competent, basically the catalytic converter looked like this in cross section. And Engelhard made the catalyst that goes in here, and here's the tubes for the airflow coming through. And you had to make a weld here, a weld here, a weld here, and a weld here. And they have to pass an X-ray inspection. This is like 16-inch thick titanium. And the spec said you were not allowed to flaw any larger than 10,000ths of an inch. Okay, that's about 4 human hairs. Okay? Now, where did they get that spec? Because if you take an X-ray and you use a 5 times magnifying glass, which is what most specs will not allow you to use more than a 5 times magnifier when looking at an X-ray, because if you go to 20 times, you can find the whole Rocky Mountain range in an X-ray, okay? If you go to a high enough magnification. Someone found that was the smallest flaw they could find, and that's how they decided in their specification at Boeing to say, I want a perfect weld. I don't want to have any flaws. There was no acceptance criteria what made engineering sense here. It was just what could be found, okay? And if you find anything, well, turns out welding of titanium, cleanliness is next to godliness. Fingerprints can give you enough hydrocarbon residue to create a pore on that weld, okay? And so I just gotten back from 2 weeks away. I didn't have time to go to New Jersey, and I told him, I said, how are you cleaning it? Well, we're just cleaning it in some acetone. I said, what grade of acetone? Yeah, well, just something, I said, get some reagent grade acetone and clean it in reagent grade acetone, because most acetone that comes in a 55-gallon drum, if you pour it on a glass slide and look at it, let it evaporate, you'll see Newton's rings. There'll be a film of oil on there, okay? Just like fingerprints, okay? I said, get some reagent grade acetone, clean it, and then try your welds and see if you can get better than 50% pass on your 360-degree X-ray. Well, they tried for a week, and they called me back, and they said, you got to come down. We're still not passing. And I had to be down in New Jersey for something else. I said, well, if you can stay until 6 o'clock at night, I'll come by after my other business down in New Jersey, and I'll look at things. So they stayed, and I went by, and I looked at their operation, and I said, well, how are you cleaning it? And they had not gone to get any reagent grade acetone. They had not taken my advice, okay, that I gave them for free on the phone. They just said, okay. and tried to keep doing the same thing. The current definition of stupidity is to continue doing the same thing that you've been doing and expect a different result, right? So I walk through their plant and see how they're doing things, and I tell them, get yourself some reagent grade acetone. Okay, that was how I left. Well, they did, because I'd met with them face to face, right? And I told them the thing that I told them on the phone, but telling them face to face made them believe it, I guess. And they were delighted. A week later, they had only failed 1 out of 10 rather than 1 out of 2. I mean, they were just delighted. And so I sent them my bill, and they sent me a check, I guess. And 3 weeks later, they called me up and they said, we've fallen off the cliff again. I said, well, how are you cleaning it? Are you following the procedure? Well, can you come down? So this time they had to pay the whole freight of going down. And I went down and I looked at what they were doing. They quit doing what I'd told them to do, and they'd gone back to their old procedures, and no wonder they were, So anyway, I told them a third time how to clean it, and I guess 747s are flying. But the real problem here was someone at Boeing had written a stupid spec. Just because you can find a flaw doesn't mean the flaw is harmful, okay? So here's an example of a specification or a standard that should never have seen the light of day, okay? And it was gonna tie up getting this entire aircraft out the door because someone was just writing a CYA spec because they didn't know anything any better. Well, there's a lot of specs out there, which gets down to this question of, is the design to code or the specification good enough? Well, if you've got a well thought out and well peer-reviewed code, like the boiler and pressure vessel code, it's been around for 100 years and has about 300 or 400 people on the committee, and those people will keep each other honest, then actually that's a pretty good code, and it's a good thing to follow. It's maybe not always good enough, but usually it's good enough. But when you got one guy fresh out of school who went to work for Boeing, doesn't understand anything about fracture mechanics or non-destructive testing, and he's told to write a code, he writes a code, a specification that requires people to do things that are just a total waste of money. Now, I appreciate the total waste of money. Okay, in this particular, actually I didn't have time to go down there, but anyway. So after those stories, let's talk about inspectors with a little I and a capital I. Anybody have any idea what I'm talking about with a little I and capital I? Pardon me?
I don't know. The only big I know is like Inspector.
There is Inspector Gadget, okay? And if you got Inspector Gadget, then you don't need codes and specifications. Well, that's actually a good definition here. If you look in the structural welding code,
there's a certification for an inspector.
There is, exactly. Good. That's another good answer. It says in the structural welding code, all welds shall be visually inspected. Does that mean that the capital I inspector has to do it? No. Okay. That means that someone has to inspect it. Who's the person who usually inspects with the little I inspector? The welder himself. He looks at it and he can tell if it looks like a turn on a plate, it's probably not a good weld. Okay? If it's nice and smooth, it may not have full penetration depth or anything else, but it's got a chance of being a good weld if it looks good. Okay? So far as that goes. But in fact, the code requires certain types of capital I inspectors. And if you look in I'll just use the structural welding code, but you can do this in the boiler and pressure vessel code as well, or many other codes. This is under inspection, chapter 6. Okay, contains all the scope. Remember, these things tend to include things like scope. Okay. Contains all the requirements for the inspector's qualifications and responsibilities, blah, 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 okay? There's the contractor's inspection. There's the verification inspection. Those of you that worked in shipyards or other places, or you will, there's the contractor's inspection. If you're at Bath Iron Works has their own inspectors. They have their own welders who are supposed to look at it, and that's a little I inspection. And they're not doing the structural welding code, they're doing some Navy spec, but nonetheless, there'll be something where the contractor, the people building the vessel or the ship or the bridge or whatever, they have their inspectors running around, okay? But there's the verification inspection, okay? And the verification inspector is someone like Lloyd's Register of Shipping or Bureau Veritas or American Bureau of Shipping or the U.S. Navy soup ship, okay? That's the verification inspection. The contractor's inspection, they may have to inspect 100%, they may have to inspect 10%. For different welds, critical areas, there'll be different requirements. The verification inspection is sort of a quality control, quality assurance. So this is quality control, if you will. This is quality assurance inspections, and there's different categories. And it turns out in this case, you're absolutely right, the capital I inspector has to be a certified welding inspector if you're going to do it to this code, which is another way for the American Welding Society to make money, okay, by certifying welding inspectors. But it's actually a very worthwhile thing, because now you have a national standard, another standard that's come along in the last 15, 20 years, that everybody knows this person has met a certain minimum level of qualifications to be a welding inspector, okay? They've taken a test. So there are little I inspectors and capital I inspectors. This is my terminology, but if you look at the boiler and pressure vessel code, it gets to be very, very specific about who this inspector can be. And in the boiler and pressure vessel code, there's actually a whole organization, which I mentioned before, the National Board of Boiler and Pressure Vessel Inspectors is an organization that basically goes around, because these boiler and pressure vessels have to be inspected like every 3 years. Depends on the state. And each state has different laws and different requirements, but a typical average is about every 3 years you have to have a guy go in and pull things away and look at things. Now, some of those inspections you get to be fairly involved. You have to remove the insulation if it's an insulated pipe. Now, they don't have to inspect everything, but they have to inspect enough, and there are standards. There's a book this thick that tells them what they have to do to meet the inspection. And they can tell the owner, you got to remove the insulation on this area of pipe so I can look at the pipe underneath, and I can look at how pitted it is. There's something called corrosion under insulation, which is a big problem because you get moisture builds up in there. And I've seen a number of failures because of corrosion under insulation. They were going to go in there with an ultrasonic thickness monitor, see how much wall thickness is left on that pipe, because it can corrode internally too. And there's certain limits, and it has to be inspected. Now, one of the problems is it's often a lot of work and a lot of expense to go remove insulation. Or I have a situation right now up here in Salem Harbor where they had a 40-year-old boiler for a utility plant generating electricity, and for about 15 years the Massachusetts state inspector decided it was too much trouble to make them clean all the ash off the manifold header at the bottom of the boiler. And they had this ash that was built up several feet deep. And they were getting corrosion under ash, if you will, okay? Not under insulation, but it's the same type of attack, okay, where you collect moisture and stuff. And what he should have done is, this was a critical area. It said so right there in the boiler code, that this was one of the areas had to be inspected on a regular basis. And every 3 years for about 12, 15 years, he decided, oh, we'll wait till the next time to do it, right? Until it blew up and killed 4 guys, okay? And then of course there's a lot of times with a little money under the table, save money so you don't have to, go to that expense of removing all the ash or the insulation and things like that, okay? There are other things where, remember the boiler and pressure vessel code, I showed you under scope how it would exclude human-powered vessels or human-occupied vessels, and I showed you how it would exclude your home hot water tanks, okay? Well, one of the exclusions was anything that operated below 210 degrees Fahrenheit. Well, where did you get a number like that, 210 degrees Fahrenheit? Well, it just happens to be two degrees less than the boiling point of water, right? So there's this company in Tennessee that's making manwich. Anyone ever had a manwich sandwich? You know, a little tomato barbecue sauce you mix with some ground beef, huh? Right? My grandson loves it, okay? Well, they're making manwich, and they have this thing that's really a stainless steel hot water tank, if you will, to hold the steam that, well, actually it's supposed to be water, but it's not supposed to be steam. That is going to, if the manwich line stops, you have to keep it above 180 degrees, because if it drops below 180 degrees, those little bugs can start growing, and my grandson's going to get sick when he eats his manwich, right? In order to stop the line for an hour or two, if something's gone wrong, they have this hot water tank that's supposed to keep the manwich tank warm above 180 degrees. Well, there might have been some problems with the controls or whatever. This tank was made out of stainless steel. It's a food processing plant, so what do they do to clean everything? They use bleach, right? Because it's a great disinfectant for all those little bugs. What does bleach do to stainless steel? It corrodes it, okay? And so what happens underneath the insulation? Well, if some of that bleach gets underneath the insulation, you've got corrosion going on underneath the insulation that no one can see, and no one takes the insulation off to remove it. This vessel looked like, you know, a dried riverbed in terms of all the cracks that were all over it, until it blew up and killed a couple of people, okay? So the inspections have to be done with some common sense, and the inspections can end up costing some money. But a lot of the inspection requirements are there because we have a history. We have a history that someone got hurt once somewhere, and we have these codes growing in size, doubling maybe we'll come up with a Moore's law for specifications and codes, how many years it takes to double, right, in thickness. But there's lots of problems. Now there are certain other rules about, I gotta find the book that I brought that is in. The chain of management control. Yeah, okay, this is it. Okay, there actually are managerial rules for if you got a manufacturing plant. This is out of an overview of the non-destructive testing handbook, okay? So if you're interested in non-destructive testing, I've got a nice little series of books. It's about 9 volumes, and it takes up about 20 inches of shelf space. But you got the general manager of the plant, you've got the chief engineer, who's responsible for design and manufacturing processes and product specs, and you've got a purchasing agent who keeps everybody from spending money. He's the preventer of, you know, like Dilbert, the preventer of information services. The purchasing agent is the preventer of productivity, okay? You have a plant manager who's in operations, and you have a quality manager. Many of the codes require that the quality manager report to the head of the business and cannot report to the chief of operations. Why? Because there's an obvious conflict, okay? Why do we have soup ship in addition to the shipyard inspector? Because you can't have the fox watching the hen house, okay? So this is just something out of their things, but you have a chief inspector. This is the capital I inspector, and he may have other capital I inspectors with him. They report to a quality manager who can go to the general manager to beat up on the plant manager if the plant manager refuses to do what they say, and the general manager is the one who's got to arbitrate between the operations guy and the quality guy. And that's how, if you go to soup ship, you will have the pleasure of spending half of your life in meetings where people are sitting there arguing over, was this acceptable or not, okay? And things like the good old Boeing spec over here, okay? Does the spec even make sense? And the nice thing is, half the time, it doesn't, okay? Someone just created it out of whole cloth, but it's there. Okay. Any questions on this stuff? I'm going to switch gears right now and go back to design a little bit. So we've gone through lots of things on codes and standards, but let's go back to design, because many of the codes actually have design rules. The boiler and pressure vessel code has specific design rules. The structural welding code has, chapter 2 is always on design in the structural welding codes. There are different types of design. One is conceptual. Another is architectural. Now this really, what I'm going to do here really comes out of sort of the building or bridges, okay? Steel construction type design things, making something big and heavy, so far as that goes. There are some others, but what's the difference between conceptual design and architectural design? Yeah.
I guess would be that conceptual design sort of takes requirements and doesn't worry so much about feasibility, sort of puts things together in a broad stroke.
Yeah, exactly. I mean, you got some concept, you're going to build a cable-stayed bridge that had never been built before. We have cable-stayed bridges now, but if you went back 25 years, we didn't. And so you had a conceptual design that you're going to be, rather than having catenary bridges with big cables, which is like the Brooklyn Bridge or the Verrazano Narrows or the San Francisco Bay Bridge, where you just hang a cable between two towers and you drop some cables straight down from that and hang the roadway from those cables. The cable-stayed bridge is like the Bunker Hill Bridge, where you actually have these tension, cables, and you have a bunch of them, and it makes this what some people think is more pleasing architecturally concept. It makes a more beautiful bridge. And the Bunker Hill Bridge over here, basically each one of those towers is topped like the Bunker Hill Monument, okay, if you haven't noticed that. But the cable staying, that was a technology developed in France, where they actually use sensors to tension each one of those cables, because let's face it, those cables have to be equally tensioned or properly tensioned. If you had one of them that was highly tensioned and the others were slack, well, the highly tensioned one is holding up the whole bridge and it's going to snap, right? So actually the thing that made that technology viable was this technology the French developed of when they install the cables before they finish the bridge. They basically put sensors on them and they tighten the cables as they keep on building the bridge to balance the cables, so that they bear the load in a shared way as intended. Yes?
Do they continue to be vested after the bridge is built?
I don't think so. They may go back and check from time to time, but I don't know that there's not a continuous adjustment like every year or anything, and I'm not sure. I don't know enough to say that they don't go back after 5 years or 10 years just to check it. But it's sort of it's a fatigue-loaded situation, but the tension in the cable should stay fairly constant. Plus, there's a big safety factor in these things, okay? Safety factors, tomorrow's lecture, Dr. Belmar will be here. And safety factors take care of a lot of mistakes. So while you were talking, I was crumpling up paper. This is a conceptual design of an MIT building. Can anyone imagine what building?
That weird looking one on the other side.
The Stata Center. Okay? Frank Gehry, one of the world's top architects. He does concepts, okay? He doesn't worry about details. And if you've been through the inside of the building, you'll realize he doesn't worry about details, okay? He does concepts. And I actually heard this story from Vicki Sirianni, she was head of the MIT physical plant. She's an architect, her husband's an architect in downtown Boston. She was head of MIT's physical plant. And I used to, when I was department head, I used to give at Christmas time, since I get in early in the morning and I park right over here where the nighttime custodians punch their time clock at 7 o'clock. I knew a lot of them. I'd get in at 6 or 5:30 or whatever. And so I knew a lot of them. And so I started when I was department head to give them a Christmas breakfast between 6 and 7 in the morning. Now we had to do it on the clock, and I had to get permission from Vicki, because a lot of these people work 2 or 3 jobs. You know, they work nighttime at MIT and they finish the job here at 7 o'clock and they go to another job, they start at 7:30, right? I mean, that's just the life of some of these people. So anyway, we used to give them an appreciation Christmas party, and people used to say, why are you doing this? You're a department head. Well, do you know we got better service at a physical plant in the department when I was department head than any other department. If you show appreciation for people, they will respond. Anyway, so there was a reason why we did it. Anyway, Vicki had come back the day before, this brother, thinking about the concept of the Status Center, and they had hired Frank Gehry because this was, Chuck Vest was president of MIT, he wanted to leave some legacy, okay, to MIT. And the Status Center was going to be the building that he was going to leave. It was supposed to be a new main entrance to MIT on that side of campus. You know, we had 77 Mass Ave, but this was over by the subway station, and they'd built the Whitehead Institute and the biology and all this other stuff. And here we're going to have the Status Center. And so Frank Gehry, one of the world's top architects, designed the Bilbao, Spain Art Museum, the Art Museum in Los Angeles, which is the Getty Museum. Okay, these titanium surface structures and stuff. So Vicky's sitting in his conference room in Los Angeles the day before, and he comes in and he starts crumpling up paper and throw it in the middle of the table. He says, that's what your new building will look like. So the Status Center's concept was crumpled paper. So now as you look at the Status Center, you will understand why it's designed the way it is. You had an idiot for an architect. Okay. And you paid them a lot of money. I mean, the building was supposed to cost $150 million. It came in at $430 million. All of us took a pay freeze in like 2003 or 2004 to help pay for that building. So every time I walk through that building, I'm thankful. Okay. Has anyone been in the? Some of you have been in the building, right? So what are some of the design features that struck your eye? The first time I went through several things. I've only been on a couple of floors, and I don't like to go through the building very often.
Can't find my way around. Nothing makes any sense.
Okay, well that's MIT. I mean, it fits right in with the rest of MIT. So, okay, that's right. A good point, but okay, I think that I can say that about a lot of MIT buildings.
Well, there's no real uniformity. Like normally when you design a building, like you want to have all your bathrooms in the same spot, so it's easy to like
Yeah.
figure everything out. Like there's no uniformity. Everything's just kind of on something. It's probably difficult.
Yeah, okay. Well, I mean, I just kind of walked through the lobby and I looked down at the floors. Anyone looked at the floor in the lobby? This is a $400 million building. It's bare concrete. I think they put some lacquer on it. But have you noticed the gaps between the concrete slabs? I mean, I had a ruler in my pocket or whatever, I think at the time, or I went back with a ruler in my pocket a couple of days later. There's a gap, a 1/16 of an inch gap, and it's at about 3/4 of an inch deep. Whoever designed that has obviously never swept a floor. Do you know what will collect in the 1/16 of an inch? So it's really healthful too. Okay, the other thing I noticed, along with the concrete slabs and the concrete block wall, which they did paint, by the way, what's the furniture?
Plywood.
Plywood, custom built, 1 inch thick plywood with 20 laminations per inch. Do you know what this cost? No wonder it costs $430 million. We have custom built plywood benches at a price that's 50 times any other bench that you could have bought out of a catalog. But the students can sit on those, right? And the other thing that's good about plywood, aside from the fact it doesn't warp, you can't refinish it. You're just going down through the laminations, right? You just have to live with anyway. Okay, and then I got over to the lobby where they have, what do they have for a coffee shop? Starbucks. Now this is there for the students, right? There are a lot of students here who spend $3 a day for a cup of coffee, right? But then turn around from the coffee shop and gaze upon the restrooms, the doors to the restrooms, and they have water fountains. How many water fountains are there? 5 water fountains between the men's room door and the women's room's door. 5 water fountains. Now this allows for high volume. Because if you've been to an airport where they have 2 water fountains, you know the long lines that are there lining up to get a drink, right? We have 5. Art in water fountains. They're staggered at different levels, okay? I knew that my pay raise had been well spent when I walked through there the first time, okay? Which brings us to the next level of design, which is called detailed. So it's conceptual, architectural, which someone comes in and they say, okay, we're going to use a certain size beam, okay? Because we've got typical floor load in a building today for human occupancy, and you're not going to be doing manufacturing, might be 100 pounds per square foot, okay? So manufacturing building, maybe you need 150 or 200 pounds per square foot as the load because you're going to have heavy machinery or something in there. But typical floor loads are going to be, for this building probably has 300 pounds per square foot capability because it was designed by a bunch of concrete junkies back in the early 1900s. But they didn't have the fancy computers. But if you go through the American Institute of Steel Construction manual for different, there will be column shapes. They call them W shapes for I-beams. And so this is a W14 by 30, weight per foot, 455. W14 by 455, that's pounds per foot, okay? Is that right? Yeah, must be. These are big beams that I just happened to open to.
Isn't the number on the side?
Oh, down here. Yeah, okay.
14 by 12.
Yeah, okay. It's this number down here. Weight per foot is by 22. Okay, 22 pounds per foot. That's not such a big beam. Okay, 14 would be a 14-inch web height, and you can get different weights of these beams, and they'll give you the section properties. So if you're a civil engineer, you just look in this manual, and it tells you someone else has already done the thing. But the architectural, it'll be a conceptual design. Says we're going to have so many floors. We're going to have so many. We're going to have a shape of the building that fits this footprint. It's going to have, if it's a big skyscraper, we'll top it off and it'll look like this on the top, and you can go look downtown Boston and see how people have done different things. The architectural design is where some architect or draftsman or civil engineer gets in and says, okay, if we're going to have this floor load, we need to put in this size beam, and this is how many beams, and how, and what type of spacing and stuff. But they just put in a beam. They don't tell you how you're going to connect that beam to the other beams. So there will be a drawing. Anybody ever seen these types of drawings? I mean, it's the same type of thing on a ship. You're going to have some concept. It's going to be a littoral craft. It's going to be a submarine. It's going to be an aircraft carrier. There's some concept. There's some architecture that basically lays out the geometry. So this is, if you want on a ship, this is the CAD system design. But in the CAD system design, you don't have the welds. You don't have the bolted connections. You don't have the clip angles and all this other stuff. You just say, well, I'm going to have this size beam. I'm going to have this type of bulkhead, whatever. The detailed design, which might actually follow on from the CAD system nowadays, is where someone goes in and says, okay, this is the size weld I need here for this type of shear loading, or this type of tension loading, or this compression, or I'm going to put a clip angle here. Because I also have to worry about another type of drawing, which are the erection drawings. And anytime you're building a big thing like this, you have to know what sequence you're going to put it together. And particularly, you're building a building in downtown Boston. You don't have a football field next door that you can lay down all your I-beams in order to let them sit there until they're needed. You actually have to have them delivered like every half hour during the day, and you lift them right straight up off the truck, by crane to the top of the building, and you got to bring them in the right order, okay? Because if they're not, you got a problem of where do you store these things. The erection drawings will tell them, when to plumb the building, okay, when to, you know, what bolts to put in, what torques, you know, whatever. So you're getting to finer and finer detail. And then there's a last set of drawings. Anybody know what the last set of drawings is? When you finish building the building, someone goes back to say, well, how do we actually build it? Did we do it this way? And the answer is invariably no. There were changes made along the way. And so many times, the contract will require that the contractor provide a final set of drawings, which are the as-built. Because sometimes someone goes back after they need to do a repair or something, and you can't go on the assumption that it was built as it was designed. Because in the real world, people run into conflicts, problems in the erection, in the detailed design, and they find a way around it, or they decide we're not going to put that system in, we're going to put another system in this area. And when you go back to figure out how it was built, you can't use the original drawings. You need to, if you hopefully have a set of as-builts. Okay? Yeah.
So when I was a navigator on my last ship, when we went through the Panama Canal, I took the as-built drawings.
Yeah.
We had to give the Panama Canal Authority so they can calculate all your measurements.
Yeah.
And that when I was showing it to them, they pulled out the Jane's Fleet, the book.
Yeah.
And they said, well, why are your measurements different? I don't know if I can trust these. Yours is 7 inches longer than this one, than it's supposed to be. That's how it was built.
Well, and did they let you through?
Yes.
Did they charge you extra?
We gave them cookies.
Oh, okay. Bribes work, okay? Okay. I mean, but okay, the point is, things are not always the way they're supposed to be. And that usually is not a problem, but there is actually a fairly famous problem, the Hyatt Regency Hotel in Kansas City. So you know something about it.
Yeah.
You from Kansas? No.
Civil engineer undergrad.
Oh, okay.
Studied this one.
Okay, you already studied it. So what happened?
Some about the,
If I put up something like this, does it help you?
yeah, the rods
Right.
that were supposed to be the drawing on the right. It's one solid rod's not the right term on the
Yes, well, it actually was a rod. It was a steel rod that was supporting those of you that have been through Hyatt Regencies, they have these huge lobbies. They go all the way up 30, 40 floors, and people can go out and they can look out. Great place to commit suicide. I grew up in Atlanta when they built the first Hyatt Regency, okay, in the world. And people would just go down to walk through and see this huge lobby. Well, in the Kansas City Hyatt, they had walkways that went from the ends, where the rooms are. They had walkways at different levels, okay? And so this might have, I think the Kansas City Hyatt, I've been there, and this was about 20 stories tall or something. And they had like 5 or 6 different walkways at different levels from different floors. And you could walk across a shortcut, okay, path through the middle of the air, right? You're walking in the clouds. Yes, go ahead.
So they were supposed to put it together the way on our right there. With
Yep.
the cable going straight down from the upper walkway through the lower walkway down to the bottom. But those beams, those rods proved difficult to install, so they instead did it the way on the left, which created some sort of stress concentration.
A shear right here. This little distance between here creates a shear load. This was straight tension, right? Tension through the rod. The rod was sized properly, but not for a shear load on this little box beam. The box beam was already welded together, okay? And so that's why you couldn't just kind of put the clamshell together. And these were supposed to be threaded rods, and someone was supposed to, on the bottom one, or the top one, or whatever, they were supposed to have nuts. You can barely see the nut. There's a little nut under here. And so someone was supposed to thread the nut on for 20 stories. How'd you like to be the guy who gets to turn the nut? Okay. Talk about carpal tunnel syndrome. So someone in erection decided that's too complex. Let's do this. And they just didn't bother to tell any of the design engineers who were probably incompetent to begin with. Now, there is a procedure that if there is a change, it's supposed to be signed off by all the engineers. Okay? Everyone up through the ranks is supposed to sign off on this change. Well, that didn't happen here. Okay? So there's a whole story here in civil engineering of there were checks and balances in the procedure, but they didn't follow the procedures, and so no one learned about this problem. And it really was the connection failure that failed was not the rod, it wasn't the bolt, it was basically the C channel, these two pieces of C channel just sheared. They didn't, because you had a type of loading, a shear loading on them that was never designed for by the designer. Now, I've seen the same thing on roof collapses in buildings in Pennsylvania. We had a snowstorm back in the 80s in Pennsylvania, which was the 300-year storm. Okay, go to the Weather Channel, they have stories about this storm. I had worked for the next 2 years on roof collapses, okay, when you have a big snowstorm like that, okay. But in that particular case, it was, they had gotten this was before computers got quite as sophisticated, and you're going to learn about safety factors tomorrow, but the building safety factor is 1.67. I mentioned that once before, okay? And that 1.67 came about historically. People found that was good enough that we didn't have lots of buildings falling down. In the early 1980s, there were some steel companies, some mini mills, decided that they would go into making bar joists for roofs, okay, for malls and shopping centers and places like this. And they could beat the system and sell lighter weight joists if they started doing things like, if this is your bar joist and it's got it's a truss, and it's got, it's got some, this is open spaces. These are angle steel or rods or whatever, and they found that instead of making the whole thing like 3/4 of an inch thick steel up here, they could make it. Let's see, how does it go? It can be thinner over here and thicker up here, right? So they would start welding steel on steel to take up the bending stresses more efficiently, and they would be taking weight out from all the people who had been building bar joists before, and this was going to be their competitive advantage. And they could calculate these things in computers, because computers were getting more powerful in the mid-80s. You had PCs that had disk drives with 20 megabytes of storage, okay? They had 128K of memory, okay? These numbers may sound a little silly to you, but that's what we had back then. Anyway, the problem was you could model a perfectly symmetric system in 1985. You could not model an asymmetric beam. And so what happened in one of these things is, in order to actually make the thing, there was a little gap in here. The computer program had everything, all three of these things coming together at a point, but in fact, one of them came in here, and the other one came in here, and there was a shear load in here, similar to the Hyatt Regency. And that's why the building came down. I mean, you go and look at the beams after the snow load, and the thing just sheared. It's like someone put it in a vise and pushed on it, okay? Same type of thing as the Hyatt Regency, shear loading in the as-built. So little changes, seemingly minor changes. If you're not the stress designer, it may not seem important to you, but it can be very important to the piece of steel, okay? And the steel wins, they get the ultimate vote of what they can carry. So anyway, 114 people died in the Hyatt Regency collapse, 200 were injured. And today the building is still there. The lobby, however, their lobby is 2 stories tall. And they built another building beside it, and so you check in the other building, and the area where this 20-story lobby was, where everybody died, is now filled in. There's nothing there any taller than a ballroom, okay? Because who wants to be in part of a lobby where 300 people got injured, right? But in any case, so that's the Hyatt Regency collapse, because the as-built wasn't the same as other things. Okay, no questions on any of that? If you ask questions, I'll think of another story. Okay, the other story I want to talk about right now is levels of inspectors. Oh, wait a second, I have some other things here. But I do want to talk about levels of inspectors, and then we'll go to other things. If you will, in the American Society of Non-Destructive Testing, there are 3 levels, very cleverly named, Roman numeral 1, Roman numeral 2, and Roman numeral 3. And an inspector who has a level 1 inspection certificate, he might have been working for 6 months or whatever as an apprentice, and he's learned how to do certain things. But a level 2 inspector is probably someone who's a lot further along, several years, and has taken some tests, and everybody has to take tests to do these things. And so it's sort of like the apprentice and the journeyman, if you know plumbing, things in the codes and trades. And you would think that level 3 is someone who's even more sophisticated, right? In non-destructive testing, right? No, doesn't work that way. Level 3 is the management guy. He probably doesn't even know how to turn on the machine, okay? So level 1 is a guy, he's an operator, and he knows how to operate the machine, but on the basic level. Level 2 is the highest proficiency level you can get as an American Society of Non-Destructive Testing inspector in terms of proficiency of running the magnetic particle or the ultrasonic testing or whatever. Level 3, this guy keeps the paperwork. He's a clerk. He's often the owner of the inspection company, and he likes to say, I'm a level 3 inspector, okay? And unless you happen to know the business, you don't realize that that just means he's a clerk, okay? He shuffles paperwork, okay? Not that paperwork isn't important. I mean, someone has to send out the invoices and cash the checks, okay? But he probably doesn't know squat about how to do an inspection, okay? But I see this all the time where some guy will say, I'm a level 3 inspector, okay? And people who are not in the business think that's really something, okay? It's not anything. It's actually something less than the others. And in fact, I didn't bring it with me, I don't think. Remember I had this interpretations book from the American Welding Society on the structural welding code? There are some questions there about level 1, level 2, and level 3 inspectors, and whether a level 3 inspector can actually perform an inspection. And the code says, no. They haven't been trained. They haven't been tested, okay? A level 3, keep them out of the shop, okay? Let them stay in the office, okay? That's not the way they answered it exactly, but that's the bottom line. Okay, so you should be aware of those types of things. Other examples of screw-ups that have happened because the engineers don't talk to the mechanics and others. Back about 20 years ago, Ford came up with a new air conditioner compressor for the Ford Taurus. And this was a very clever design, and there was a single piston that shuttled back and forth. It acted as 2 pistons, if you will, okay? You had two cylinders, but a single piston shuttling back and forth. So it was just a cylinder with a single piston, but you were compressing one side while you were sucking in on the other, and then you compress that other side while you're sucking in on this side. But in order to make it work, there were some very, very precise machining tolerances, like a fraction of a thousandth of an inch on the clearance to make this thing work. So the engineers at Ford had conceived of this new, less expensive compressor design because fewer moving parts but greater precision in assembly. And they knew that when they machined the cylinders, that they had to do it properly, because if they weren't flat, if they had a bend in them, a bow in them, the piston couldn't go back and forth, and the tolerances are so tight. And so they wanted to send it out for prototype. They sent it to a machine shop. It might have even been a Ford machine shop. I don't know that much of the details of the story. But they sent it out to the machinist with a fixturing on how to hold the cylinder when you're actually doing the reaming and lapping and grinding of this cylinder. And they got the prototype back. It worked great. Went out and spent $100 million to build a line to make lots of these air conditioner compressors. I happened to buy a Ford Taurus that year in February, and come May, I go to turn the air conditioner on, and it doesn't work, okay? And I go to the Ford dealership, and I say, my air conditioner doesn't work, and they said, oh, yeah, you know, they look at it for a day. Well, actually, yeah, I guess in this case, they looked typical. How can we inconvenience the customer? We'll make them bring it in so that we can diagnose it, and then we'll make them bring it in another time so that we can fix it, and then we'll have them bring it in a third time. Anyway, you know, if you've taken your car back to a dealership, you know what I'm talking about. Anyway, so I bring it in, and they said, oh, it needs a new compressor, but Ford doesn't have any. I said, what do you mean Ford doesn't have any? I haven't heard they quit selling Tauruses. Well, what it was is they had found a problem in the production. They found lots of these things not working, and they basically were making sure that all the new compressors that they had fixed were going to production so they could sell cars. And those of us who bought a car in February, tough luck, they said, oh, well, we may have a compressor for you in a couple of months. Oh, gee, I can now run my air conditioner in September, right? This is great. That's not, so I said, you know, the car's under warranty. I suggest that you get me a whole new air conditioner or a whole new car if you like. Okay, this could be a Massachusetts lemon law, and I did take a car in on a lemon law once back in the 80s and won against General Motors. But anyway, they finally got me a compressor. It was early June. I finally got my air conditioner going. But then I learned the story behind this from a friend. What had happened is they built this $100 million line, and they had designed the fixturing just like this engineer had designed the fixturing so they could do the machining. And then they started finding that nothing fit, and they weren't getting their clearances, and they went back and started tracking down what was the root cause of this. And someone went to the machinist and said, well, did you machine it with this fixture? He said, oh no, I knew that wouldn't work. I changed the fixture. So the prototype worked because the machinist knew that what this engineer had designed was crap, and so he fixed it. He just didn't tell anybody that he had fixed it, and Ford spent $100 million building a plant based on the crappy design. Okay? The point of this is it helps to communicate. It helps to have some respect for the hourly workers out there who are actually doing the work, and sometimes they know a heck of a lot more than the engineers, right? So anyway, that's another story on poor communications and failures that result therefrom. Okay. Now, what I wanted to talk about for a little bit was how failures lead to code changes, and this is basically Henry Petrosky. I mentioned him before. I brought this book in. So in the early 80s or mid 80s, he's a civil engineer at Duke University, and he wrote this book and he has something in here about the Hyatt Regency and mostly civil engineering things like bridges and buildings, famous failures of bridges and buildings. And his thesis in here, to engineer is human, comes from to err is human, right? And his thesis is that the only way we really progress in the world is by failure in engineering, okay? We build a bridge, we build it a new way, it collapses, and we decide that's not a good way to build it, okay? You know, there's the Verrazano, the Tacoma Narrows Bridge, the Galloping Gertie, you've all seen that vibration study and things, where only the dog died, but there was a casualty, it was the dog. But in any case, there are lots of other studies that will talk about how codes change. One of these, and next Monday we'll have class, which may be the last class. One of my students got this out of the MIT library when the library goes and sells old books that no one's checked out in years. This is the 1946 report on design and methods of construction of welded steel merchant vessels, report of an investigation, 15 July 1946. This is the Liberty ships, okay? This is the story of the Liberty ships. It has great photos in here, some of which you have not seen before. There's the famous photo of the Schenectady sitting at dry dock. Okay, this is in many textbooks nowadays. Okay, of a Liberty ship just sitting at dock, minding its own business, and along comes a crack, and it just splits it right in two. And this is the Schenectady. But in fact, it's not the best one. The best one is to look at the Esso. This is the Esso Manhattan, where it happened in the middle of the North Atlantic. I'd rather have it happen at the dock, okay, if I was you, if you're going to split the vessel right in two. And the statistics on this is 4,694 welded steel merchant vessels were built by the Maritime Commission in the United States and considered in this investigation. 970 of the vessels out of 4,700 suffered casualties involving fractures. That's a pretty high failure rate. 24 sustained a complete fracture of the strength deck. 1 vessel sustained a complete fracture of the bottom. 8 vessels were lost. Of these, 4 broke in two and 4 were abandoned after fracture occurred. 26 lives were lost, blah, blah, blah. Okay, so after World War II, 3 places in the world decided to figure out why these ships failed. One was the Naval Research Laboratory and a guy named William Pellini. William S. Pellini was chief of metallurgy. When he retired from the Naval Research Lab, he came to a place called MIT Ocean Engineering Department, and he wrote this little pamphlet on guidelines for fracture-safe and fracture-reliable design of steel structures. Another place was the British Welding Institute. The United Kingdom decided they needed something to look at why these things failed. And the reason that talks about welded vessels, and this doesn't talk about welded necessarily, but and the third place where a lot of work went on was here at MIT in the metallurgy department with Professor Cohen and Averback and some others. I TA'd for Professor Cohen in the 70s, but he was a big-time metallurgist. He worked on the Manhattan Project during World War II. Anyway, Pellini and the Naval Research Laboratory came up with a new spec that all submarine steels had to meet called the explosion bulge. Essentially take some big heavy plates, you cut a hole in it that's probably about 1 foot or 16 inches in diameter, you put a plate on top, you set off an explosive charge on the test plate and try to drive it through the hole, and if it cracks in an acceptable way, the steel is good for building naval ships. Here's one that fractured like glass, not acceptable, and these are increasing temperatures actually. This is 160 degrees Fahrenheit where you actually form a dome. You're explosively forming this dome before it cracks. And so even today, surface ships don't use the explosion bulge test, but the nuclear navy still does, okay? Very expensive, probably $100,000 a pop, okay, to qualify your materials. But just like Petrosky and the civil engineering failures and that, if any of you haven't seen this book, Great Naval Disasters of the 20th Century, okay? It's sort of fun to read. Gives you 3 or 4 pages on disasters going back to the Spanish-American War and things. So what great naval disasters do you know of in the last couple of minutes? But that's not really that's a maritime, that's a civil. I mean, I'm thinking actually, when it says naval disasters, it means U.S. Navy, okay?
The Edmund Fitzgerald, was that structural, or was that just they got?
It was, the Edmund Fitzgerald was a coal carrier in the Great Lakes, and it failed. I can't remember exactly the reason it failed, but it took a lot of lives with it. It was bad weather and a number of other things. I don't know if it's a structural failure. It's a lot of bad weather. You don't know any of the...
What was like the errors were the Port Royal or the Lemoore County or those ones?
The Scorpion, Thresher, the who? The Maine. Oh, well, Spanish, yeah, if you go back to Spanish American, the Maine, where it explodes basically I guess the explosives blew up. And so they, after every one of these, there are new codes and standards. That just like after the Liberty ships, they came up with the explosion bulge test, okay? And other people picked a lot of these things up. So Petrosky's whole theory is that we progress by failures. Something fails, we go and study it, and we then do something else to keep it from happening again. You don't know the Belknap disaster in the Navy? Yeah. Yeah, I probably have talked about it. Have you already gotten that far?
Or maybe it's in the video.
It's in the video. You've gotten that far in the video? Okay, fine. Okay. But the Belknap is when it was a destroyer Belknap ran into the John F. Kennedy on one of its early operations. It hit it right below one of the hangar deck, or the elevators that takes the aircraft up to from the hangar deck to the flight deck. And some of the jet fuel landed on the Belknap and started a fire in the aluminum superstructure, and the Belknap was toast. And the joke in the Navy at the time was a couple of gallons of aviation fuel would wipe out any capital ship in the fleet. Okay, this was not long after the British Sheffield, which got hit by an Exocet missile, and it's a cruiser, and the whole thing, aluminum fire in the superstructure, and wiped out the whole ship. Okay, so back in the mid 80s at David Taylor Annapolis, this place that is closed now, someone said earlier, they were doing a lot of stuff to replace aluminum superstructures with waffle steel so it wouldn't catch fire. Okay, and I've actually had several students do papers on, well, the Thresher and the Belknap, not the Belknap, but the aluminum superstructure fires. And if you go to the web, there are people still debating whether the aluminum caught fire or not on the Sheffield and on the Belknap and stuff. But I guarantee you that NAVSEA thought it did, or they wouldn't have been spending $100 million to figure out how to make high-strength steel waffle membrane construction to get rid of the aluminum superstructures. But today, what are your littoral ships made out of? Aluminum, okay? So I guess a couple of gallons of jet fuel will still wipe out any ship, right? You just don't want to have anyone get that close to you with the jet fuel, okay? Huh? Pardon me? What?
There are helicopter pads out on those ships.
Oh, well, yeah. There's actually lots of things. But, hey, if it's just a helicopter pad, those are small. Okay. Well, Dr. Belmar will be here tomorrow. I'll be here next Monday. And then the live lectures will be done. Kathleen, you got to figure out, are you guys doing the problem set, or are you doing the presentation?